Good afternoon. Thank you for this opportunity. Lockheed Martin and IBM are proud to be elite sponsors of what has been a fascinating discussion so far. I can't stand at a podium. I can't sit in a chair. I've got to keep moving, so forgive me in advance. A lot of the discussion has been data, the path from data to trust. And I'm going to share with you some of the Lockheed Martin journey in the area of autonomy, which is exactly that. How do you, in real time, collect data, digest data, develop understanding, and make very important decisions in very small amounts of time? And that's kind of the journey at Lockheed Martin for autonomy. Just for definitions, right? You know, I think the Defense Science Board was pretty close, had it about right. Autonomy is a system that can compose and select a course of action to accomplish a complex goal. And that can be, there's a spectrum of human interaction with autonomous systems. From dumb old systems, which are fully human controlled, to human in the loop, to supervisory, where the human is on the loop, all the way to the human is separated from the loops, and now there are many loops. Think swarms. There's 1,000 loops that the human couldn't possibly be on, but is managing the whole group of. And the value proposition for autonomy, well, and just one common theme through that, is that humans are involved. And the interaction between humans and autonomous systems, I think, is a very rich and important area for us to work through. You're seeing this in self-driving cars, and I assure you, you're seeing it in our aerospace sector. The value proposition for autonomy is kind of obvious and clear. Humans are great if the task is under 8 hours and more than a second. They say the very best video gamers can make 5 decisions a second. Ask my wife, that's not me, you know, no way. 1 decision an hour, but 5 decisions a second. So the value proposition of an autonomy system that can make 10,000 decisions a second is very compelling in a wide spectrum of applications. If you look at the Lockheed Martin product range, we have the XL UUV at the bottom of the ocean, a squad support vehicle on the land, on surface, MQ-25 refueling jets, the autonomy refueler, F-16s, and all the way to the Juno spacecraft, hundreds of millions of miles away from Earth exploring Jupiter. Each of these requires different autonomy solutions, different degrees of interaction with humans. But a common thread through these is there are large, non-attritable systems that are very important to the operator. They cannot be thrown away like the small drone. They're not the drone you buy at the kiosk in the mall. They have to be designed to operate at exceptionally high levels of integrity. Either the asset itself is so important, or there are humans on board. That the integrity with which data is analyzed, processed, and decisions are made has to be done at a very high level. Give you one example, that F-16, right? That's a product that's been out there for a long time. It now has the auto GCAS system. If a pilot is maneuvering high G maneuvers in a mountain canyon and the pilot passes out from G-lock, executing too severe a maneuver, the aircraft recognizes that in a fraction of a second, takes control of the airplane, understands the geography around it, pulls the jet up to straight and level flight out of the mountain canyon, running down through clear, safe terrain, and the pilot comes to, regains consciousness, and the airplane asks him, you know, grab the stick when you're ready, right? There have been five or six saves so far where that system interacted with the human got saturated, I'm out, the system detects it, teams with the human, takes over a task the human can't execute, and then transitions back to the human. Those transitions between autonomy and human control are a fascinating and kind of growing technical area and something we're very focused on at Lockheed. In the part of Lockheed I work for is Sikorsky Aircraft. We make the Black Hawk helicopter. We make a 19-passenger commercial helicopter. And it's fascinating. In our journey, we're putting autonomy into all of our products. It can grow the capability of the product, improve its safety, and improve its economic value proposition. This is our version of a drone at Sikorsky. Again, it's not the small thing you got under the Christmas tree at Christmas, bought at the kiosk in the mall. It's a 12,000-pound twin turbine helicopter that carries 12 passengers, has 2 crew up front, is FAA certified. We've put an autonomy suite into this to make it safer and more capable. When we started our autonomy journey, that helicopter has a pretty big cabin. When we started, the computation required to do what we want to do filled the entire cabin. No passengers, all computer racks, and you would have to fly with the doors open to cool the computers. Not a very useful product. Then we monitored it, it got down to 1 rack, and when we started flying Sarah, our Sikorsky Autonomy Research Airplane, the supercomputer was the size of a microwave oven. We use our open architecture standards, commercial best available computation, and we've just upgraded the computer and it's the size of a toaster. Now, we don't need a smaller computer. That's a 12,000-pound helicopter. It can deal with the size of the toaster. Now, it's just going to ride a curve of capability. More and more computation firepower to make more and more complex decisions in real time. Interesting, we've demonstrated this technology in both a helicopter and an airplane. Let me show you, if we could run the video. Let me show you a video of this airplane. And we intend that it is piloted, right? So here's an early flight where we have Mark Ward, our pilot. He's not using cyclic, collective, and pedals and things like that. He's putting in large mission commands into a tablet. Any of you in this room, and probably those of you who are not helicopter pilots would do better than those of you who are helicopter pilots, could fly this helicopter. You'd command a takeoff. It would say, confirm takeoff now. Yes, please. Rise into a 40-foot hover, show you the map, and let you select a destination. And it would do all the computation required to fly through national airspace. And during that flight, most importantly, it's doing all the emergency procedure calculations. The supercomputer is jamming through, using a vision system, understanding all the terrain, computing the emergency landing procedures if it needs to, several times a second. If something happens, if the crew is incapacitated, if you lose engines, the helicopter's already pre-planned the optimum trajectories and how to respond. This helicopter is crash-proof. If you're flying it and you're using the tablet and you command it to fly into that building, it's about to fly over a bridge on the Merritt Parkway, it will not enable the crew to fly into terrain. And if you think about helicopter missions, they spend most of their time where they add value is in that obstacle-rich, close to the ground environment. Think, this is a helicopter that might save you on Route 95 in that dark, stormy night after a car accident. It's going to EMS you to the hospital. That's an obstacle-rich, in the wires, in the trees, bad weather mission where a crash-proof helicopter becomes very valuable. That technology, the supercomputer, which does some of the high-end algorithmic thinking, combined with triplex fly-by-wire flight control computers, is architected to do complex non-deterministic thinking in the high-performance computer environment, more open architecture. And then it's got a highly deterministic core flight control, which is kind of the never enable those simple errors, the fly into terrain, those fundamental functions, to fully enable those at all times. So it's an interesting mix of non-deterministic and deterministic functionality, which we are convinced will help the flight crews build trust in the system. They'll have the higher order system providing great advice and the lower order system giving them reliable results that they count on every time. That technology is flowing into the Black Hawk helicopter. It's been fascinating for us. The interest is just as high in the commercial sector. Many helicopter airplane operators very interested in single pilot operations. There's a looming pilot shortage, increasing air travel, and they would love to have single pilot operations. And the Sikorsky definition of that is if you lose the pilot, everyone on board survives. The airplane executes emergency landing procedures, completes the mission, returns to base, all depending on preset conditions. And we're really building that level of trust in a system that can be certified. It's been interesting. There's a lot of talk of drones, urban mobility, a lot of companies in this space. Lockheed is doing what I call the mind-numbing, painful, years-long work to rigorously certify the architecture and the software to achieve the level of integrity that we've kind of been talking about all day. And to enable the system to fly with 12 people in the back, 19 people in the back. In the case of Black Hawk, 12 troops in the back, and fly into that dark, stormy night, deliver troops into that rough canyon in some of the harshest conditions. So, you know, it's an exciting adventure, but very demanding and difficult to get to that rigor of certification. The requirements for future vertical lift, the big program of what might be next for rotorcraft, are just starting to come out. And I think DoD has shown a lot of vision. It's a high-speed reconnaissance helicopter, low noise, able to survive in a very complex threat. And it's optimally piloted. Isn't that an interesting word pattern? They want a vehicle where the commander can decide, today I want 2 crew up front. They're going to be controlling multiple off-board assets, but I want them to ride in a vehicle that can fly itself, and those 2 brains will be thinking more about the tactics of the mission, the strategy, operational curiosity, but they'll be riding in a drone that they are mission managing, and they will be collaborating with other drones that may include the same vehicle type, where that vehicle has been switched into 0 crew. It's decided that 1 aircraft of the flight will be manned and 4 will be unmanned, and they will collaborate with other assets. Again, stretching and taxing that data management, data collection, and certification, qualification rigor that's required. These products, whether it's a US Coast Guard flying off Alaska to pull people off a ship in horrible weather conditions, Air Force Combat Search and Rescue, rescuing a downed aviator, or plucking someone off a roof in Hurricane Katrina. Protecting the lives of the people on board these products is worth so much, and the autonomy technology can now enable that. It provides that crash-proof functionality, the ability to do emergency procedures, and offloads those crews in that very high workload missions. So I appreciate that chance to share the Lockheed Martin autonomy journey. It's going across all of our products. It's changing the interaction between humans and machine, and doing the very rigorous work to enable certification and qualification of these systems so they can be trusted by the passengers and crew of them. Thank you for your time.